first I'll be looking at what was Darwin dealing with when he was forming his theory. And he was born in about 1809, so this is pre-industrial revolution, before a lot of democratic reform in England. So that has a lot of influence on how people see the world and how people see each other in relation to the world. After that, I'll be talking about some fundamentals of evolution for those who may not know as much. And after that, I'll just touch on the modern influence of religion and basically the state of how the public views evolution today, which isn't exactly the same as how we view evolution, obviously. So my key questions, I would like to ask questions, are where did this theory come from, and how does it work, and then how do we feel about it? And the last question is something I think is very much underrepresented, and it's not asked as much as it should be, because that's what everyone else is asking, and that impacts which research is funded, what's taught in schools, and everything else that impacts how science is done. So really, we should be asking ourselves this question, so we can actually talk about it with other people who don't have a science background. So yeah, I like to think of each concept as a tree. So it's just a mental model I use when I'm reading about something new, especially in science. I think first I want to find out about the roots, and that would be the foundation of where the theory comes from, the work that was done before it, the cultural attitude that affects how the theory develops, and then the trunk, of course, is the background knowledge that you need to understand the theory, as well as the theory itself. And as for branches and leaves, that would be individual disciplines and individual pieces of data that are collected. And it just helped me figure out where I am and how fundamental a piece of information is, because you need some kind of framework to put new information in before you can understand it properly. So our roots would be the origins. So here are two pictures of Darwin, and the last one's actually a photograph, as this was taken about 1854 or so. When he was young, he grew up the son of a doctor, a rich doctor, and he grew up loving nature, loving to run around outside, collecting everything, and his dad tried to correct that, but it didn't work very well, as you can see. And in fact, his summer job at the age of 16 was working as an apprentice doctor in his dad's practice. And that didn't work out very well. But nevertheless, his father sent him off to medical school that same year. And he managed to get through about 2 years before his dad realized this wasn't going to happen. Because while he was at medical school for 2 years, he found out that lectures are boring, religion doesn't belong in science, as heresy, by the way, and he found out about this natural history group, kind of like a student society at school. And what these students did is they got together to challenge orthodox religious concepts in science. They challenged the presence of religion in science altogether. They challenged current explanations about how the world works. They were called radical evolutionists, not Darwinian, but the whole concept of things changing was really new. Because, like I said, this is pre-industrial revolution. A lot of England was farmland. A lot of people had the same life as their parents, and there really wasn't a lot of change. There was just a natural order to things. And that naturally extends to how they view the natural world. Species just exist. They were brought into existence by God. They were created about 10,000 years ago, and they're not connected to each other in any way. They just exist separate from one another. So the concept of extending our family tree to include all of those other species was just unheard of. And one more thing about our relationship with nature. In Christianity, there is a separation between man and animal, and this was on full display. So, and this is actually something that Darwin shied away from tackling very well during his lifetime, because it is such a touchy subject. It even is today. People don't want to think about being related to a chimpanzee. They might be okay with the chimpanzees and gorillas being related, but the moment you get to talking about them and human beings, it's a whole different story. It's a whole different level of personal emotion. So that's what he was dealing with in medical school. And right after that, his dad realized this is not going to work. So he sent him off to Christ College to become a parson, because, well, what else are you going to do? So, against all the odds, Darwin managed to not find it boring and graduate. But by then, he had already discovered the bug collecting craze, so he collected insects all the time. Somehow graduated. And he found a mentor, one of the biology teachers. And that professor got him a placement aboard the HMS Beagle, where he was going to serve as a geologist and naturalist on a 2-year survey trip around the world. So that's really where the roots of his theory are, is in that trip, and to a certain extent in his exposure to the radical evolutionists at university. And by the way, that photo is about 1854, as I said, and his sideburns offer, I think, about 40% more analytical ability. I think I read that somewhere. There's no other reason he would have them. So here's the route the Beagle took. And it took 5 years, not 2, because there's no real science done if you don't miss at least 2 deadlines. You think I'm kidding. So we start up with Plymouth, and then we go down past Africa, hit the tip of South America, work your way down, and you go all the way to the other side of the world. And they were mostly visiting islands and relatively little-known coastlines. So while the Beagle was charting the coast, Darwin's responsibility was to spend as much time on land as possible and document the local geology. And because he hasn't grown up, he also collected these huge natural collections of, fossils and natural plants and animals and all that. And he didn't have very much experience with animals other than insects, for obvious reasons. So he really just popped those up and sent them off to England at regular intervals so they could be examined by real experts. And this is just an anonymous illustration from about 1874. It's interesting in that you've got a primate wearing a suit over here, right beside Darwin. And this was actually, might have been inspired by a famous quote by a bishop who was at a debate with one of Darwin's disciples, as it were. And, someone ended up saying, "Are you saying my grandmother was a monkey?" And then, "I would rather have my grandmother be a monkey than be related to you." And it went down. So the concept of being related to any of these things was an insult. So shoot, I just missed about 1/3 of it. Anyway, I'll fill you in now on the rest. Darwin spent about 15 years after that voyage as a popular author. After he published his journals, he was an acclaimed geologist. So he spent a lot of time on geology, studying barnacles for 8 years straight. And as soon as he finished that project, he got back to natural selection. And then he started really developing his theory in the 1850s. And as it happens sometimes, scientists kind of think the same way and they arrive at the same conclusion. And this is what happened to Darwin. He got word that there was a naturalist in Brazil, Alfred Wallace, who was developing the same theory. So they decided to jointly publish a paper. And I think Darwin had it a bit more correct, honestly. But either way, it didn't get very much traction. There's only one review of the paper that Darwin ever remembered. And it essentially said what was true wasn't new, and what was new wasn't true. So that's a going review right there. Needless to say, there was more. He published a small book. You might have read it. It's called The Origin of Species. And
what was the name of the book about barnacles on?
I have no idea, and I don't want to know. Anyway, so now we get into the fundamentals of modern evolutionary theory. Now, this is different than Darwinian evolution because there's more of it. Because Darwin was only concerned with natural selection, investigating natural selection, improving natural selection as a force of evolution that was, not governed by God. And later, scientists discovered DNA. Let's figure out how that works. For a while, they weren't sure if Mendelian genetics would fit with evolution. Now they discovered this very well. For a while, they weren't sure about population genetics. Now they discovered that fits very well as well. And so the modern synthesis is just evolutionary theory, not particular to Darwin, although he provided the core of it. It's been very much expanded in the century or two since he was alive. So there are four main forces of evolution. The first would be natural selection, of course. This is what Darwin was studying. And what natural selection is it's external pressure. So given variation in a species, where that variation either has a positive, negative, or neutral effect on that organism's survival and ability to reproduce, given all that, natural selection is the force that comes in and natural selection is the force that comes in and decides which traits are positive, which traits are negative, and anyone who doesn't make the cut doesn't get to live. So your natural selection might be temperature, it might be humidity, it might be your organism's ability to deal with high amounts of stress, or it might be their behavior. And whatever manages to survive is favored. And whatever manages to survive until the next generation is a positive influence. And that trait will stay for generations until it's no longer useful, and then it will be eliminated. So, and a good example, a very simple example, is antibiotic resistance. So say you've got a diverse community of bacteria, and you can see you've got blue ones and we've got orange ones in the first circle. And then you introduce an antibiotic. That antibiotic is going to kill all the blue ones. If there are any orange ones, it might kill some of them, but some of them will survive. And in step 3, those surviving bacteria will reproduce and divide. And then soon you have a totally new colony of superbacteria that don't respond to antibiotics. So that's an example of a pre-existing trait happening to be very good for an existing condition. And then in the case of bacteria, in a forest circle, they can also transfer their genes to other bacteria and transfer that antibiotic resistance. So it's like having a zombie. Once you've got one, you're screwed. Another concept is mutation. And this is really the raw material that evolution works with. And this is what was developed during the 20th century and 21st. What we've got here is a series of strings of information. Now, these are all the same protein, and protein is really just a long string of amino acids. These are all the same protein from different animals. We've got rats, rabbit, pig, human, and they're all compared. And you can see that some of them are very similar to each other. You've got many many amino acids that are conserved. Conservation just means that there's pressure for them to stay the same, and therefore they don't change as often as the organism is evolving. It's something that the body says, no, let's keep that, we kind of need that to live. So you can see that a lot of the bases, a lot of the amino acids there are really conserved, and you've also got strings at the beginning that are more variable. And at the bottom you've got a little bar graph, and the higher the bar is, the more similar the set of data is, and the more conservation there is. And this is just a visualization that's commonly used in bioinformatics and genetics when you are comparing different species and trying to find out what's more closely related to a given string. And this is really helpful when you're trying to build a tree, for example. If you put all of your data into one program, it'll give you something like this. If you put it into another program, it'll give you a tree. And those visualizations are very useful. And next we've got genetic drift. This is one of my favorite, that's really embarrassing. But it is one of my favorite things to think of because it's interesting. And what genetic drift is chance. It's literally just chance. So you know that you have one copy of your genome from your mom and one from your dad. Now, on your mom's copy of the genome, say you've got a gene that has a mutation, and say your dad doesn't have that mutation on his copy of the gene. So let's imagine that the blue marbles in that jar are your dad's copy, and the red ones are your mom's copy. Now imagine you've got a very small population where they have those two variations of the gene, or we can call them alleles, 50-50. Now, when you're producing the next generation, what you do is it's a 50-50 chance that you're going to get either red or blue, but it's 50-50 every time. And what that means is that, say you shake up marbles, pick one out, happens to be blue, then in the jar for generation 2, you're going to put a blue marble. Now you put the marble back in, shake it up again. This time you draw out a red one, and you're going to put a red marble in the jar for generation 2. And keep going. But you don't get a 50-50 distribution because this is all chance. And what that means is that in this example you have more blue marbles than red marbles. So you're even more likely to get a blue one next time, which means that over time the red allele is completely eliminated and you will never see it again unless it reappears spontaneously. So that's how you can lose information in a population. And a great example of this is just human beings, honestly. What can happen is that in our history, humans have migrated to every place on the planet, pretty much. And when that happens, what you have is a small population, what we call a bottleneck. And in a small population, the little nudgings of chance and just random allele selection become a lot more powerful. So you start off with a reduced gene pool because you don't have a representative sample of the diversity of the population you left. And furthermore, the alleles that aren't very well represented are much more likely to be eliminated. So that means that if you have a population that's been constantly migrating and sending off little bits from place to place, then their genes will be much more similar than a population that just stayed in the same place and cultivated the diversity they had. And you do see that in the human population. Europeans are a lot less diverse than Africans. Genetic diverse. And then we've got my very favorite, gene flow. Now, this is more studied recently. But what it is when you have genes that go to a different place and increase the variation within a population. So it could be you have two islands that are far apart, but you have regular trade between these islands and you have regular interbreeding. That maintains the genetic diversity. Or you could have a population of animals that migrates to a different place and joins another group of those animals. Then they've added their genetic diversity to that second population. Or another example could be viruses. In your genome, you probably have about 200 little snippets of viral DNA, and that's just the scars from past infections. Because what viruses do to survive is they inject their DNA into your cells, and then your own machinery replicates the virus. And maybe some of that DNA gets left behind, and that is gene transfer. This is gene flow. But this example, these aren't the actual colors, it's false color, but these are mitochondria. And you might remember that mitochondria produce energy for our cells. You have a whole lot of them in your muscle cells, a little bit less in your neurons. And these mitochondria, these organelles, actually have their own genome. And if you sequence that genome, you find out that they're related to bacteria. This is an example of a symbiotic relationship. Way back before we were multicellular, when we were predators, just swimming around, we would find a bacterium and we'd engulf it and we would digest it. That's what we ate. And one day, at least twice, for 4 times in our history, we didn't digest. That little bacterium stayed there, and we learned to develop a symbiotic relationship where we give them nutrients and they provide us with energy. And it's been that way ever since. Now we can't live without them. It's the same way with plants. I mean, how did they learn to harness the energy from the sun? They got it from their chloroplasts, which used to be bacteria. And what this means for the tree of life, this gene flow, is that it's less of a tree and more of a web, where you have some interaction between even different domains of life, drastically different species interacting and passing their genes to each other, and their genomes are learning new things. So I think that's pretty cool. It's much more complicated than Darwin could ever imagined. So if you zoom in far enough, then you would see that we are right here. We are Homo sapiens. We're right here. If you trace this line back to a node, then that would be a speciation event when our ancestors split into 2 groups, group became us. And if you keep following that back, you find that each species has a unique genetic history on this planet. Now, if you zoom out, we are right here. It's a little humbling, isn't it? If I took all the labels off, I could point anywhere on this diagram and you wouldn't know what I was talking about. I could point to equal eye, I could point to athlete's foot, and you would not be able to tell that I wasn't talking about our species. Every species has its own history, every species has been evolving for the same amount of time, and every species' history is interesting. So we're really not that special. And that's a consequence of evolution that we just kind of have to deal with. So here's where I get into the public response, because if you're a scientist or if you're science-minded, then you might look at that and think, oh cool, we're part of this giant network of life. But if you have been raised to believe that you're special, then you feel something very different. You might feel angry. You might feel just instant denial, shut down a conversation. And if you're emotionally invested in a different story than the story that evolution is telling you, because that's what it is, it's a story, then you're just going to have a really hard time accepting this story, especially if it means discarding the one you've grown up with. So here are the consequences of unguided evolution that are easy for some people to deal with and not easy for other people. So for one thing, there is no end goal or purpose to our existence. So there's no end goal. Evolution is not going anywhere. It's just kind of happening. It has a very limited vision. It only sees what's right in front of it. And we are living proof that something in life managed to avoid all the obstacles so far. So we're living proof that it's possible to exist here, and that's pretty much all we can say about it, because we didn't control anything that happened to us. And not only that, there's no purpose to our existence in particular. There is no purpose to parasite's existence. They just kind of adapted to the circumstances and they got really inventive. There's no purpose to the existence of E. coli. It's a bacteria. It does things. There's no purpose to our existence. We're able to talk about why we don't have a purpose in life, but that doesn't mean that we have a purpose in life. It just means that we have really good brains. And this is hard to swallow. Because part of our pattern recognition that we've evolved to have for our own safety and survival is that we tend to see meaning even when there is none. And this even extends to how scientists talk about evolution. They might talk about how something is designed to do this or it evolved to do that. And even then, that started agency and consciousness to a process that is unconscious and unguided. And that's just a human trick that we have in order to think about something that's even happening. So not only is there no purpose to our existence, inherent purpose, we're free to create our own. There is no evidence of a supreme being in charge. And I like the answer that Stephen Fry gave, the pastor, when he was asked about, what would you say if you got to heaven and you had to speak to God, and then Stephen Fry said, how dare you? How dare you make children with bone cancer? How dare you make all of these horrible things and make it look like pure chance, as if you were never there? And I kind of feel that way as well. But when you're raised with a story that has divine intervention and miracles and constant acknowledgement that there is a God, then faced with the evidence that most of life has never even heard of this God and wouldn't recognize it if it saw it, then it can feel kind of disheartening. And then you're not sure how to build your new reality because the center of it has just been torn away. And I do understand that. And the last part, we are not special. We really aren't. If we disappeared, nature would probably have a beer and then just go on. Whereas if nature disappeared, then we would be gone. We would not survive at all. If you get rid of half of our gut bacteria, we will be gone in 2 days. So yeah, we are not special, but every day you have something telling you the opposite. You know, you're here to consume, you're here to pollute the planet, you're here because you're made in the image of God. How much better does it get than that? You're made in the image of the supreme being that rules out the universe. Does that mean you're better than the organisms that aren't made in the image of God? Does that mean that you get to do whatever you want with them? And this is the paradigm shift that had to happen for Darwinian evolution to gain any ground. Because remember that when Darwin was growing up, things were created, mankind was above all that. And Darwin had to say no to everything. So here I've got, you can see that here I've got the percentage of adults who say they are religious. A lot of data is missing from Africa, unfortunately, but the countries mentioned there are their example. So the darkest blue would be over 90% of adults say that they are religious. And the redder you go, the fewer people say they're religious. So you can see China is very secular. South America is much more religious. We are less religious than the United States. And that has consequences for our beliefs in evolution, actually. And so if I give you some quick numbers to compare, say you look at the UK, which is very neutral, honestly, on the diagram. In the UK and in Canada, about 2/3 of adults would say that they believe in evolution. And about 20% would say that they believe in creationism. And the rest can go either way. They're not really sure. Now, in the US, the number is very different. 51% are creationists, and the remainder are pretty much split between not sure and unguided evolution. So that was surprising to me. I didn't know that the numbers for creation were so high. And if you want a third example, in Egypt, where it's very religious, only 8% of adults believe in evolution. And again, it's because once you have this story, you have to discard anything that doesn't fit it. If you can't fit it, it has to go. It's a question of which is more important, the evidence and where scientists say it leads, or what your pastor says, or what your mom says. And this is an interesting quote because back in 2008 or 2009, the Church of England formally apologized to Darwin. He's dead, so he didn't know. And they said, sorry, we've mistreated you. We'll do better. And what I like in that letter is that they did acknowledge that protecting evolution is seen as a litmus test for faithfulness in some Christian communities. And they regretted that fact. But this letter was, well, for one thing, this letter was met with confusion from everyone because secular people and Christians alike were saying, you're probably just doing this to counteract all the bad publicity you've had lately. And then the more conservative outlets, such as Creation, and this is quote from creation.com. That's one of their foremost authors. Creation was saying, this is a complete affront to Christianity as a whole. You've already compromised by accepting an old earth. And this is, I think, to why many Christians find it difficult to reconcile evolution and their faith. Because Isaiah spoke of the coming Messiah as literally the kinsman redeemer. Without the common descent of all mankind from Adam, the whole kinsman redeemer thing is completely worthless. It doesn't exist. So if we evolved from primate ancestors, where's the cutoff for what is human? Why did Jesus come when he did, if he did at all? And so it completely removes your sense of perspective. If you're forced to look at global history, 3.5 billion years, give or take, then what's happened in the past 2000 is really just a blink of an eye, and it doesn't really matter. And that is a direct challenge to Christianity as it's taken literally. Some people are able to do the mental gymnastics to reconcile this. Many people are not. And I hope this is just a brief overview of how this came to be and what it's generally about. I think that outreach like Darwin Day is important because if the public doesn't know why this is important, then education doesn't get done, and research doesn't get funded, and then free speech is at risk. Because if there's anything that needs to be protected, it's the ability to tell someone else what it has no meaning. Because that is an affront to how we feel. That's an affront to our personal sense of self. And it's even supported by evidence. And if we can't say that, then there's really no hope for anything else. As far as free speech goes. And in closing, I would say you're special, just like everybody else. Have a nice night.